Let's discuss diffusion coefficients for vapor and liquid binary mixtures. There are estimated diffusion coefficients for both of those phases. For vapor, it's approximately 10 to the negative fifth meters squared per second, and for a liquid, it's 10 to the negative ninth meters squared per second. Now, these are both estimates of a vapor and liquid diffusion coefficient. Sometimes you'll run into a case where you need to determine the actual diffusion coefficient. There are a couple ways you can do that. One is the Lennard-Jones potential. Now, this Lennard-Jones potential, what it does is it looks at the intermolecular forces in a vapor to help you determine that diffusion coefficient. This equation involves your diffusion coefficient from A to B. That's equivalent to the Boltzmann's constant K, which is, in this case, 0.00266. Next, you'll have your temperature to the 3/2 power of the system, and that's all that's in the numerator. In the denominator, you have the pressure of the system, as well as the molecular weight of A and B to the 1/2 power, your collision diameter of A and B, as well as your collision integral. The collision diameter is squared. The collision integral is based on the boiling point temperature, and it can be estimated using T star. The equation for T star is the Boltzmann's constant multiplied by the actual temperature divided by the energy of molecular interaction of A and B. This will determine your collision integral, as I said. But this entire Lennard-Jones potential will give you your vapor diffusion coefficient. You do want to remember units. Units are always important. The diffusion coefficient is in centimeters squared over seconds, or meters squared over seconds, depending on what you want, but it comes out to be centimeters squared per second. So keep that in mind while you're determining your diffusion coefficient. Make sure to convert any pressures or anything else in the equation that might change that final number or unit. Now, for a liquid diffusion coefficient, you're going to use the Stokes-Einstein equation. Now, this equation was derived from the drag equation of a sphere flowing through a liquid atmosphere. The Stokes-Einstein equation is used in a dilute system, and this does affect our diffusion coefficient. A dilute system is when you have two components. B, in this case, is going to be in very high concentration, and it's going to be a salt-like solute, with component A, which is going to be an extremely low concentration. B is so high in concentration that A almost doesn't exist, and both are a salt-like solute. So our diffusion coefficient, AB, is going to be an infinite diffusion coefficient because, it's very high concentration of B. And our diffusion coefficient is equal to the Boltzmann's constant multiplied by temperature over 6 pi, which is just constant number. And that's going to be multiplied by our solute particle radius of A, the smaller in concentration, the lower in concentration component, multiplied by the viscosity of B, our higher concentration component. In some cases, you don't have all the components for the Stokes-Einstein equation, and we can use a different equation in order to create an estimate of the diffusion coefficient. That's called the Vin's equation. Now, the Vin's equation is, of course, an estimate, and what it involves is finding the diffusion coefficient for AB, and it uses the infinite diffusion coefficients. So infinite diffusion coefficient of AB to the power of the less concentrated component in this diffusion coefficient problem. So let's say for this diffusion coefficient, the less concentrated component is A. So that's going to be the mole fraction of A. And that's going to be multiplied by the diffusion coefficient of BA, infinite of course, to the power of the less concentrated component, which we'll say in this case is mole fraction of B. And that's the estimate of your diffusion coefficient for a liquid. This estimate can then be plugged back into the Stokes-Einstein equation, so you now can find the components for the Stokes-Einstein equation. That's pretty much all you need to know so far about the diffusion coefficients for a vapor and liquid. We have determined how to get the actual diffusion coefficient of a vapor and a liquid, as well as to determine the components of a liquid diffusion coefficient using the Vin's equation. From here, we're going to derive the equation of continuity for component A going through a unidirectional system with rate of formation RA. Now, rate of formation RA, that's equivalent to essentially the accumulation of flux through a system. So when we're thinking about this problem, we're thinking of the accumulation equation, which is in minus out plus accumulation. You see that a lot in heat and mass transfer. Accumulation. Yeah, let me spell that right. So we're going to be thinking about a cube. And this cube, of course, has multiple directions. So let's first draw that system. This cube has our z direction, z to dz, our x direction from x right here to dx, and our y direction. And that's going to be our y to dy. So our flux is flowing through this cube. So the flux of component A at z goes to the flux of, moves out and becomes the flux of component A from z to dz. So going into the cube, if we're writing this equation out, we have our flux of A, z, and you also want to consider the volume of the cube. That's very important because the rate of accumulation, first of all, the rate of accumulation is per volume. Yeah. So it's over volume. The heck? Sorry about that. So for this one, for this flux, we'll consider multiplying it by dx dy. And we'll subtract from that our flux of component A from z to dz. And add on our rate of accumulation multiplied by our volume, dx, dy, and dz. And our flux of component A coming out of the cube from z to dz will also have a volume multiplied by it. So dx dy, once again, that RA multiplied, or rate of formation multiplied by the volume. So this equation is equivalent to the change in concentration of component A multiplied by the volume, dx dy dz. And since it's a flux, you want to think about it per time. So we'll have our change in time underneath. Let's remind ourselves that we're trying to derive the equation of continuity, which is of course already known, and the equation of continuity is the diffusion of the flux of the flux of component A plus the derivative of the concentration of A with respect to time minus the rate of formation of A, and that's going to be equivalent to 0. So now looking at our derived equation, I can see a lot of the components from our continuity equation are similar to one that we just derived. What I want to do is try to get rid of that volume or that we've put everywhere in this equation. So we're going to divide everything by dx, dy, and dz. And that's going to get us our flux of A at z divided by dz minus our flux of A dz over, of course, dz, plus our rate of formation. This volume is going to be completely canceled out. And that's going to be equivalent to our change in concentration of component A over our change in time. And we're already closer to that equation. Let's just combine terms from here. So we have our flux subtracted by our flux at a different distance, all divided by dz, plus our rate of formation is equal to our concentration over our time. What we have right here is the change in molar flux rate, but in negative form because it's in minus out. So we can rewrite this part of the equation as the change in molar flux rate over the change in our z direction. This is negative, plus our rate of formation is equivalent to our change in concentration of A over our change in time. So now let's subtract everything over to the other side, and we get 0 is equal to the change of concentration of A divided by our change in time, plus our change in molar flux rate over dc, plus our rate minus our rate of formation. And this is equivalent, this equation that we just derived is equivalent to our equation of continuity. We just derived our equation of continuity. It does look a little different. Of course, there's d's in certain derivatives in certain areas, and there's this diffusion part of our flux, but this is the same thing as the change in our molar flux rate. So now we're going to introduce how the equimolar counter-diffusion arises of a vapor-liquid interface when the enthalpy of vaporization is independent of composition. So we pretend we have a diffusion column. Diffusion column, huge, all right? We zoom into our diffusion column. You see your bubble. Got a bubble. Let's make that a better bubble. We've got a bubble. This bubble is surrounded by liquid. Now this bubble is full of vapor. Yay! And right here on the bubble, the very outside, the interface of the bubble, the vapor and liquid are in equilibrium. This is the VLE, vapor-liquid equilibrium. That doesn't look like an E. So at this equilibrium, vapor is condensing into liquid. So vapor transforms into liquid. And when vapor transforms into liquid at that equilibrium, the enthalpy of vaporization is released. So now liquid, right? In the liquid over here, there's a bunch of energy that's just been released. So the liquid will then vaporize back into vapor. And now there's this equilibrium. Wow. So it's just going back and forth. There's basically zero exchange, right? So the vapor's turning into liquid, the liquid's turning back into vapor once that enthalpy of vaporization is released. With this knowledge, we can write an equation. We have our molar flux of our liquid phase of component A, right? And we're going to multiply it by our change in enthalpy of vaporization, or like that's going to be your vaporization energy. We're going to add this to our molar flux of our vapor phase of component A, multiplied by our change in enthalpy. This should equal 0, right? We just discovered that it's an equilibrium. The liquid will become vapor, the vapor will become liquid, enthalpy will be released, and it becomes 0. From here, we know that these changes in enthalpies cancel each other out. It's change in condensation versus vaporization going in one direction versus the other. So we can just forget about those. They're the same thing. And now we have that our molar flux of our liquid phase of component A is equal to negative our molar flux of our vapor phase component of A. So now what if we have a situation where component A transforms into 2 of component B? So it's no longer equimolar. Well, if you have your component A transforming into component B, we know that our molar flux rate, and we're talking this in terms of molar flux rate, we know that our total molar flux rate is equal to the molar flux rate of component A plus the molar flux rate of component B. It's going to be our total. So here, our molar flux rate of B is equal to -2 of our molar flux rate of A. Here's there's 2 more B than A. So plugging that into this equation, we get that molar flux rate of A plus -2 molar flux rate of A is equal to N. And so that's going to get us the negative molar flux rate of A is the total molar flux rate. Huh, interesting. That's very interesting. Now let's use this in another scenario similar to this one where 3A goes to B. How does our molar flux rate of A transform now? Well, we have that our molar flux rate of B, instead of it being equal to -3 component A, we have -1/3 molar flux of component A. And again, we know that N molar flux rate of A plus molar flux rate of B equals the total molar flux rate. So plugging that in, we get our molar flux rate of A minus 1/3 molar flux rate of A equals total molar flux rate. And that's going to get us 2/3 molar flux rate of A is the total molar flux rate. Wow, interesting. We've learned a lot. Look at how much we've learned. We've learned how to determine the diffusion coefficients of a vapor and liquid. We have learned how to know about the molar flux rate, how to derive the equation of continuity for molar flux rate of component A or for component A. We also understand how the vapor-liquid equilibrium phase works with the flux. And finally, what to do if we have a translation from component A to component B that isn't equimolar.